Okay, in this next lecture portion, we're going to introduce the idea of a transmission line and describe its properties and describe how it's able to delay the transfer of information. So to do this, we're going to take a circuit approach. We're going to try to come up with a circuit that can slow down information in a defined and quantifiable way. And this is the circuit that we're going to be using. So first, we have what we're going to call a transmission line. A transmission line is simply two conductors. It can be two wires. It can be two parallel plates. It can be a wire and a plate of metal, but they have to be two conductors that are separated from each other. Now, between those two conductors, we're going to define a voltage. Right, so that voltage is shown over here. Right, that is defined at any location Z at any time t. There's going to be a voltage between these two conductors. All right, and these conductors are shown here basically as these two parallel lines. Now, the other important thing is there will also be current along these transmission lines. These are, for example, wires or plates, and so we can run current along them, and so that will be defined by I. I will be also defined at any location Z at any time t. And so those are the two quantities that we're going to consider in transmission lines. Those are the A and B that I talked about in the last video that are going to feed off of each other, voltage and current. Now, the way we actually delay information is by putting in familiar circuit elements. The first one is an inductance. All right, this inductance that I've just drawn out is going to be along the one of the transmission lines. Right, it's an inductance. However, what's important is that the longer you make this transmission line, the inductance is actually going to scale with that length, right? You double the length of the transmission line, the inductance will also scale with it. We'll talk much later about why that's the case, and we'll show the math behind it, but for now, just take it at face value, that the longer the transmission line is, the larger the inductance will be. So really, this quantity L that we're going to define is going to be inductance per unit length. It's like an inductance density. And the units of that are going to be henries per meter. Henry is a unit of inductance, right? Now, a transmission line is imperfect. And so when that current flows along the transmission line, there's going to be a little bit of resistance that's impeding the flow of that resistance. And so that we're going to define with this value right here, R. R is the resistance per unit length. Same deal, the longer you make this wire, the resistance is going to scale with it. So really we should define a resistance per unit length, which has units of ohms per meter. Okay. The other two quantities are going to attach the two transmission lines together. Okay, so think about two parallel plates as a transmission line, for example, or a coaxial cable, or two wires. Ideally, they would be completely separated from each other. Current would never flow. But in practice, that's never going to be perfectly true. Even if there's two wires separated by air, air is going to have a really small conductivity to it. And so a small amount of current can flow between those two. And we're going to represent that with the resistor that attaches the two conductors together. All right. And we're going to define that with something called an admittance. Admittance is actually the inverse of a resistance, right? So a zero resistance means an infinite admittance, and vice versa, right? An infinite admittance means zero resistance. So ideally, there'd be no connection at all between these two resistors, or sorry, between these two conductors. And in an ideal case, G would be equal to 0, right? Because that would be an infinite resistance, all right? The fourth one is a capacitance that connects those two. If I think about two parallel plates, for example, and define that as my transmission line, that has a capacitance to it. It is proportional to the length of the transmission line, and so that's where this C, capacitance per unit length, comes in units of farads per meter. Units of admittance is going to be 1 over ohm meters. Right, that's going to be the admittance, is 1 over ohms. All right, so what we're going to do is think about a transmission line, again, a coaxial cable, two wires, as being a small series, a long series of small segments. Each segment has a little bit of inductance, a little bit of resistance, and then between the two segments is a capacitor and a resistor. However, In most scenarios that we're going to be dealing with, we're going to simplify this greatly and we're going to ignore two of these, right? So let's get rid of these two resistors and pretend like the transmission line is perfect. Let's start with that. We're going to be mostly considering that. And so if we do that and we daisy chain this circuit over and over again, this is what we get, right? This is a baseline of a transmission line, right? We have a daisy chaining of inductors and capacitors, one after the other. Now, let me take a minute to convince you that this transmission line can carry voltage and current, but it's going to slow it down and define a certain velocity to it. All right, let's start off with the assumption that this circuit right here is completely dead. There's no voltages, there's no currents, nothing is happening. And then you come along and you attach a battery on the left side of this. And this battery has 1 volt. All right, so we just placed 1 volt between the two terminals on the left side. All right. Now, Kirchhoff's voltage law tells us that that voltage has to go somewhere. So if I draw another path across the inductor and down the capacitor, down to this point, I've also have to get 1 volt, right? So where is that voltage going to go the first moment that I attach this? Well, there's two choices. It can either appear across the inductor or it can appear across the capacitor. One of those two things has to happen. Now let's go back to our rules about how inductors and capacitors work. All right, let me just write down the two sort of key formulations for an inductor. All right, for an inductor, the voltage equals L, the inductance, times the derivative of I with respect to time. And for the capacitor, it's the opposite. It's that I equals the capacitance times the derivative of voltage with respect to time. All right. So what these two equations mean qualitatively is that if you want to get a current across an inductor, you cannot do that instantaneously. First, you have to put a voltage, and you've got to wait until the current builds up. The capacitor is the opposite. The capacitor does not like voltage changing instantaneously. If you want to change the voltage on a capacitor, first you've got to run a current through it, and then you've got to wait. All right, so at the very first moment, the capacitor does not accept an instantaneously changing voltage. So this voltage must all appear across the inductor. So the very first moment that we connect this 1 volt, we're going to have 1 volt appearing across the inductor and 0 volts appearing across the capacitor at the very beginning. Okay? However, wait a little bit of time. This voltage appearing across the conductor, by definition, means that there must be some current that's going to start to flow, right? So a little bit of current is going to start to flow through the inductor, and where is it going to go? It's going to start to go, it's not going to go to the next inductor, because this inductor does not like changing currents. So in that first moment, it's going to start to charge up this capacitor. So a little bit of current is now starting to flow through the capacitor. As that current flows through the capacitor charges up and it starts to build up a little bit of voltage. And so wait a little bit, we maybe get 0.1 volts on the capacitor and we'll get 0.9 volts on the inductor. So we're starting to flip the order of all of this. But of course, as the charge on the inductor starts to decrease, the rate of change of the voltage starts to decrease as well. So basically, if I look at the current on the inductor as a function of time, I might expect to see something like this. It starts to ramp up really quickly, but then as some voltage appears across the inductor, and you get a decreasing of the voltage, it's going to start to keel over a little bit, and it's going to reach a saturation point. Eventually, if you wait long enough, all of the voltage, all of that 1 volt will appear across the capacitor, and nothing will appear across the voltage. But you can see that's going to take some time because two things have to happen. First, you've got to allow the inductance to convert voltage into current, and you've got to then wait for that current to be converted back into a voltage across the capacitor. And so if you wait long enough, that 1 volt will be transferred over here to the next branch, but it's going to take a little bit of time. That process will then repeat. Once you establish the 1 volt, 1 branch in, you're going to start to charge up a current across this inductor, which will turn into a current across this capacitor, and then the 1 volt will appear across the capacitor, and so on. This will continue over and over again. All right, so this is a sort of simple description of a transmission line, right? And eventually you get a steady current that's running along the transmission line through this inductance, and you get a steady voltage that appears across this capacitor, and that voltage and current is moving along the line. Now, let me just dispel one potential myth about the current, because we have this sort of second branch to the transmission line. There is a current that's also running this way. It's the same here as this current, right? So in general, I'm only drawing current as being in one of these branches, but it's really sort of bidirectional. Think about it like if I have a long rubber band and I tie the rubber band around a pole, or like a long rope in a circle that I tie around, right? If I take my two hands on the two ends of the pole and I pull with one side, I have to be pushing with the other, and vice versa, right? There's a back and forth to that. So that's what's going on when we talk about current in a transmission line. That's really what we're talking about, that the current is going out in one conductor and back in the other, right? So those two have to exist together. All right, so one of the things that you can see here is that these two quantities, L and C, are going to be very important for describing how quickly that wave is going to propagate, right? If I set a really big value of L, for example, what that means is that I can put a big voltage across the inductor, but if L is big, it's going to take me a long time for that current to build up, because if L is big, di dt must be smaller. And so I can already start to see that the bigger L is, the slower that process is going to be of converting voltage to current. The same applies to capacitance. The bigger is the capacitance, the more time it's going to take to convert that current back into a voltage. And so L and C, you can start to see, are going to impact the speed with which this wave is going to propagate, and we'll see that very soon. All right. Now, a quick primer on notation and drawing. There are a few ways that you will see in the literature and in textbooks that describe a transmission line. This is the way here, the top right one is the way I'm going to adopt in this course. I'm going to draw the transmission line as these two little cylinders. And anytime you see that symbol, that means it's a transmission line. You have to account for delays back and forth of waves that are moving. When we talk about transmission lines, I'm often going to be talking about the two sides of a transmission line. There will usually be a source side and a load side. So the source side is with this little S right here. It will have a voltage associated with it, and this RS is sort of like the internal resistance to that source, right? It's like a battery that has an imperfect resistance to it. The other side, we're usually going to terminate the resistance on the other end with some kind of a load, or L. It can be a resistor, but it can also be something more complicated, like a capacitor or a transistor or anything. But we're going to talk about that as being the load side. All right, now these other drawings you might see in other places, but I'm going to be mostly exclusively using the two bars here, or the two cylinders on the top. All right, now transmission lines, I've talked about coaxial cables and, two wires and things like that. But transmission lines are actually kind of everywhere in a sense. And so just to broaden your horizons, inside your brain, you've got ridiculous numbers of transmission lines. All of the connections between neurons are electrical carrying devices, or they are transmission lines that carry voltage and current from one neuron to the other. So broaden your horizons beyond just, coaxial cables and things like that. Transmission lines are everywhere. All right, so that concludes part 2 of this lecture on what is a transmission line. In the next portion, we're going to talk a little bit more about how the properties of a transmission line are determined.